Hey there peeps, and welcome to this odyssey, this incredible adventure known as derivation of the three kinematic equations of motion at constant acceleration. Yes, these only work for situations where there's constant acceleration. Zero is constant as well, so if we don't have any acceleration, that's zero. But if we have a changing acceleration, these don't work. We have to do something called calculus. So we're not doing that, so we'll be okay. We'll be okay. We're not going down that rabbit hole any further, to the jerk, into the snap, crackle, pop, and whatever those crazy things are called. So here we are though. We have three of them, and they're presented in this way with this kind of syntax and the subscripts right in the AP equation guide, which you'll be using quite frequently this year. So there are three. One is, and mind you that all of these have an X notation, but they could also be substituted for Y, which is a vertical direction rather than a horizontal direction. So what we have here is Vx equals Vx naught plus Axt. That's equation number one. Number two, X, which is the position, equals X naught, the initial position, plus Vx naught times t plus 1/2 ax t squared. Lastly, we have an equation that works without the variable of time. So it does handle unique situations where we can make calculations and determine values for velocity and maybe acceleration or displacement without time. So here we go. Vx squared equals Vx naught squared plus 2ax, and in parentheses, x minus x naught, which I just call delta x. This is displacement right here, okay? So we're gonna go and derive these 1, 2, and 3, and you'll see where they come from, and pretty soon we'll actually be using them, so you'll see what their value is. Hang with me. We begin the adventure now. Equation number one really comes from knowing that the slope of a velocity versus time graph yields average acceleration. Okay, here's a v versus t graph, velocity versus time. The slope is rise over run, delta v over delta t, the change in velocity over change in time. We look at the units, meters per second on the vertical, seconds on the horizontal, and we get meters per second squared. That's its acceleration. A little review. We set t not to 0 seconds. So we just like begin our stopwatch, boom, right at this moment here. And so time t will have elapsed. So what we have here is the relationship for acceleration in terms of the change in velocity over change in time, v minus v naught over t minus t naught, where t naught is 0 seconds. So we just get t in the denominator here, and v minus v naught over t is what acceleration is. Well, if we just solve this for v minus v naught equals a times t, the acceleration times time. If we just solve this for v here, v equals v naught plus at. For whatever reason, although I used the vector script over here, this is correct, your AP equation sheet does not. So we they're implied, but they don't put them in. They do put them in for other equations and not some. They're not consistent that way. I don't agree with it, but that's how it's printed out. So it's more proper to do this because they are vectors, but they do write it like this, and that's how you'll see it. But you'll also see it with that X subscript. I got rid of the subscript for simplicity in the derivations, but we can always put them back in, as you'll see when you actually have the equation sheet. Well, one equation done, two to go. Equation number two is written like this in your AP equation sheet. X equals x naught plus v naught t plus 1/2 at squared. I prefer writing it like this. Delta x equals v naught t plus 1/2 at squared. I just subtracted x naught to the other side, and x minus x naught is delta x, which is displacement. So this is actually, I think, much cooler. Again, we're going to rely on a velocity versus time graph. They're one of my favorites because there's so much information there. You can go to position versus time, you can go to acceleration versus time in translating the information, and also it gives us essentially the two equations. The first one we just saw before, and this second one over here, we couldn't really do this without it. The graphical technique is going to lead us there. So what happens? Well, we note here that the v naught t actually is represented by the area of a rectangle bounded by a v versus t graph. Okay, and the other term with the acceleration is that the area of the triangle bounded by a v versus t graph is also represented over here. If we look at the units, the rectangle has meters per second times second, or meters. Here, the units are meters per second squared times second squared, t squared. And that's meters too. So every term is meters, and that's really important because the equation would break down if the units didn't work. That's called a dimensional analysis check, okay? Or a unit check. We want to make sure that all the stuff here is the same, that we're dealing with oranges, oranges, and oranges. If an apple's in there, something went wrong. Here's our velocity versus time graph. Again, I set t naught to 0 seconds. And I have the time t over here. This is v naught. So this is representing motion with an original velocity, okay? So it's already moving at t naught equals 0 seconds. And we'll be accelerating and gaining speed, gaining velocity along the slope over here, okay? So the area here is base times height. It's a rectangle. So v naught times the base, which is t, is the area, and this is v naught t. That would, if there were no acceleration, if this were just going at a constant velocity known as v naught, then this would be the displacement of that motion, okay, of that object. And so if we block out the acceleration, that's what we get. Displacement is v naught times t, okay? The other piece here, the 1/2 v minus v naught times t, which is the area of this triangle. Let's see why it is. Well, triangle's area is 1/2 base times height. So the base is t, same as before for the rectangle, but the height is v minus v naught. This is going to accelerate from v naught to v over here. And so this height is v minus v naught, okay? This height minus this height gives us the height of this triangle, and so we could find the area, which is 1/2 v minus v naught, that's the height, times t, the base, okay? But that doesn't look quite like this yet, but it will. We just need to work with it a little bit more, okay? So from equation 1, we just did equation 1 earlier, v equals v naught plus at, okay? So we recognize that v minus v naught is equal to at. So I'm going to do a little substitution here. So the area of the triangle above, if I just replace v minus v naught with at, I get 1/2 at times t. What's that? 1/2 at squared, just like it is here. We got the equation from the graph. If we don't have an initial velocity, this term goes away. We only have the triangle piece. So this displacement is really just saying it's made up of two parts of the graph. One is the rectangle, one is a triangle, and we've seen this in Phineas's travels so far. So that takes care of equation 2. We got 1 to go. No v versus t graph, but lots of heavy duty cranking algebra. Ooh, okay, get ready, concentrate. Here it is, equation 3. A whole mess of algebra ahead, so let's get started. All right. Okay. V squared equals v naught squared plus 2a change in x, which is displacement, okay? What we need actually are the two equations that we kind of derived already, so we can use them and manipulate them very cleverly to get this end result over here that doesn't have time. So remember that 1 is v equals v naught plus at, 2 is delta x is v naught t plus 1/2 at squared. I still prefer this format versus the one that's on the AP equation guide. So from number 1, the first step is to solve for t. If I do that, I get t equals v minus v naught over a, the acceleration. Then we substitute the expression for t into equation 2. Okay, Equation 2 is this guy over here. So follow me, it's just kind of messy. Note that 2 has a t squared term in it. So that becomes this. Just the t squared term is this. Well, if I make this substitution, we get v minus v naught times v minus v naught over a squared, okay? We gotta deal with this here because there are multiple terms and there's the operation of subtraction. We actually gotta process this. We gotta FOIL it out. And so that's what I've done over here. V squared minus 2v naught times v plus v naught squared, all over a squared. Okay, that's good. That's just t squared. So we will plug that in for t squared. So equation 2 now becomes this thing over here, all right? So it's delta x equals v naught times v minus v naught over a. Okay, that's because we substituted t, this in for t. And this here is the thing that's been FOILed out with the a in the bottom. Now I've already taken the liberty of doing some cancellations in red. So I used a different color here. So we had an a in the numerator and an a squared in the denominator. So we have a over here. And I have a 2 in the denominator from the 1/2. And so what I did is I multiplied every term by 2, and I get 2 here and 2 here, leaving a single denominator with a. We have a common denominator, so that's cool. We can add things together. But even better is that what we'll do is multiply both sides by a. And so on this side, we got 2a times delta x. Now, what does that equal? Well, I've also connected things that are like terms, all right? So when I add all this stuff together over here, and you can do that on your own once you've paused this from the very beginning, you can take a look at this. I've got 2v naught times v and minus 2v naught times v, which means they cancel out. You add them, they become 0. And then I've got minus 2v naught squared and plus 1 of these v naught squared. So I get a negative v naught squared plus v squared. Okay, so what does that look like? Once I do everything, it just simplifies to this. All this stuff over here now looks like that. So we have 2a delta x equals v squared minus v naught squared. This yields v squared equals v naught squared plus 2a delta x. Yeah, we got it. Okay, so lots of crazy algebra, but very followable, very much within our skill set, expected that you can do this. All right, now the thing is we have the equations. Next step is going to be a problem-solving methodology to allow us to use them and solve and predict for situations in motion, which actually are much faster than the graphical method that we've been using. Graphical method is great. It's another way to represent and see motion. We can solve for things with area and stuff like that and slopes, but these equations will allow us to do it so long as the acceleration is constant. And so we'll see how useful they are very, very soon, and we'll be able to do some cool problems. Finally, we'll be able to discuss things like the kick of a soccer ball and a throw of a football, and we can actually apply this to sports and baseball and stuff like that, and use gravity to do some cool stuff. So these are great. Thanks for hanging with me. Morad and the 3 equations of motion out.